Hello, Mr. Kitchen, Cobleskill, Richmondville High School Physics. Today we take on Newton 1, the law of inertia. Little historical footnote, it was actually Galileo that discovered the law of inertia before Isaac Newton, but Isaac Newton wrote it down in a famous physics book called the Principia Mathematica, where he brought forward Newton's second and third laws, and because he included the work of Galileo along with his own work, ever since we've called the law of inertia Newton 1. I think most of you are familiar with Newton 1. It states an object at rest remains at rest, an object in motion remains in motion, and this tendency of objects to remain at rest or remain in motion is known as inertia. Then he goes on to say, well, this is true unless they're acted upon by an outside force, and of course this outside force is a net force. So Newton 1 is really just a special case of Newton 2. It tells us what happens when the net force acting on objects is zero. So we can write that down in our notes. Newton 1 describes what happens when the net force is zero, and that is the acceleration of objects is equal to zero. Okay, so remember, an acceleration equals zero does not mean the object is not moving. It means it isn't speeding up, slowing down, or changing direction. In other words, the objects are going to keep doing what they were doing. If they're not accelerating, they're going to maintain a constant velocity. And finally, mass is a measure, it's a number that we give to the amount of inertia. So there's a lot of things in physics that are a problem when you get them mixed up. Mass and weight comes to mind. They differ by a factor of 10, and that's a huge problem. But if you get mass and inertia mixed up, that's perfectly fine. Inertia is a concept. It really doesn't have a number associated with it. We just use the mass number for the amount of inertia. Now, in this video, I want to take on, at least conceptually, the elevator problem. And what we have in the elevator problem are really accelerated frames of reference. What happens when you're in a frame of reference that is not moving at constant velocity or is not stationary? We start out with a mass over here, and of course from Newton 1 that mass tends to, well, keep doing what it was doing. We're going to start out with a mass that's at rest. And here's our first elevator. What I've represented in the diagram here is we have a mass attached to the ceiling of the elevator with a spring. And although that seems a bit odd at first, the spring is really a scale. The amount of stretch on the spring tells us something about the weight of that mass, or the force of gravity acting on that mass. When the acceleration is zero, we call this an inertial frame of reference, and up to this point we've been working exclusively with inertial frames of reference. In an inertial frame, the force of gravity acting on the object is just going to be equal to mg, or the weight of an object is equal to mg. Things change a little bit when we begin to accelerate in the elevator. So here we've got an acceleration that's acting downward. The elevator begins to, say it's at rest, and begins to accelerate or speed up in the downward direction. In that case, the force of gravity is actually going to be less than the weight when the object was at rest. And over here, we show an elevator accelerating upward, accelerating in the positive direction. We can see from the stretch of the spring is stretched more, and the stretch of the spring is a measure of the weight of the object. So this object actually weighs more, and I think many of you have probably had this experience in an elevator. If you're standing there and the elevator begins to accelerate upward, you feel like you weigh more. Your force of gravity is more than it would be mg in the inertial frame of reference. Well, how much more or how much less depends upon the amount of acceleration of the elevator. Whenever we have accelerations, they cause forces. Forces cause accelerations. Accelerations come with or cause forces. So what we have here in green, these are the forces due to the acceleration. Now this acceleration here is negative. It's in the downward direction. So we could say, well, we have a parent force of gravity. This is F sub g prime. Let me prime this quantity over here as well. I forgot to do that one. F sub g prime is equal to mg, and we could say it's plus m times negative a, but what we usually do is factor the minus sign over here. So we say it's equal to your weight in the inertial frame minus the force due to the acceleration. And the opposite thing is true over here. If the elevator is accelerating upward, then we're going to have additional force due to the acceleration. The positive sign from that acceleration goes over here, and we have your weight in the inertial frame plus the force due to the acceleration. So that's a little conceptual explanation of how the elevator problem works. In class, we'll pick up with some numeric examples of how this problem works.